By the end of this module, you will have a basic understanding on primary pumping application, how it works traditionally, and the Danfoss solution. The key benefits of using a VLT, HVAC drive, in primary pump systems. Let me start the module with a brief description of the primary pumping application. Boilers and chillers are constant flow devices. That is, constant flow of water through the device is necessary for efficient or safe operation. In order to provide constant flow, HVAC systems are designed with two independent water loops. The two loops are primary loop, secondary loop. Primary loop provides constant flow through the boiler or chiller, and secondary loop provides variable water flow throughout the buildings to air handling units or other devices with heating or cooling coils. Primary pumps in primary or secondary systems have the task of supplying a constant flow of water through the boiler or chiller. These devices have an ideal flow rate. Flow rates that are too high or too low can reduce the system efficiency and possibly damage the equipment. The primary pumping loop provides a constant flow so that the secondary pump can tap off as required to provide the variable flow that is needed by the building's heating and cooling coils. A common pipe connects the primary loop with the secondary loop to decouple the loops, because it hydraulically separates the primary from secondary loops. In general, the connection is kept as short as possible to minimize the pressure drop. Primary pumps can be a part of primary only, or primary, or secondary system. In primary-only systems, the pumps typically provide a constant design flow through the chiller, set by a balancing valve during balancing or commissioning. Three-way valves are often used on cooling or heating coils of the air handling unit to maintain this constant flow through the primary circuit. Primary or secondary chilled water systems are generally used in commercial buildings to improve the efficiency in large central chilled water systems. The primary or secondary pumping system separates the primary production loop from the secondary distribution loop. This allows the pump in chiller's primary production loop to maintain constant design flow, while the secondary distribution pumps provide a variable flow, as the two-way valves on the chilled water coil varies based on cooling load demand. The primary pump needs to be balanced to produce the correct flow. The balancing valve on the pump discharge is adjusted to provide correct flow by adding restriction to the circuit. We shall now look at a traditional primary pumping system. In traditional method, there are two ways of achieving proper flow. Balancing valve. Trimming the impeller. First, let's see how proper flow can be achieved on using the balancing valve. In a chilled water system, the primary circuit, or loop, is equipped with pumps sized to manage the chiller's optimum flow rate. The pumps need to be capable of providing just enough pressure to circulate the water through the chiller and the rest of the primary circuit. Balancing valves on the discharge of each pump traditionally controls the primary pump flow. Adjusting the balancing valve increases the pressure and reduces flow. These pumps are often oversized due to safety margins in the design. By balancing the valve, losses are added to the pumping circuit to achieve proper design flow rate. Take a look at the illustration. It shows the opening and closing of the balancing valve. Let me elaborate on how this is done. When the balancing valve closes, the pressure is increased and the flow is reduced. Similarly, when the balancing valve opens, the pressure is reduced and the flow is increased. Take a look at the graph. It shows that, as the balancing valve closes, the flow decreases, riding the pump curve to a higher pressure and lower flow. You can also notice from the graph that, as the balancing valve opens, the flow increases, with a reduction in pressure. Now let's see how proper flow can be achieved by trimming the impeller. Trimming an impeller is the physical reduction in the diameter by machining. The primary pump flow can be controlled by trimming the impeller. The first time the system operates, the actual pressure drop in the primary loop is determined, and the pump impeller is trimmed to the proper diameter for proper flow. However, this method of achieving a proper flow results in reducing the pump efficiency. Take a look at the illustration. It shows the pump impeller without trimming. You can also notice from the graph that the pressure is high and the flow in excess without trimming the impeller. Click on the Trim Impeller button to view the changes in the energy consumption when trimming the impeller. Here, you can see the reduction in the diameter of the impeller, which will be taken in accordance with the size given by the balancing contractor. You can also notice from the graph that there is a reduction in energy consumption and decrease in flow. Now, click on the Reset button. You can see a text indicating impeller trimming is irreversible. It means that if you want the flow to be increased after an impeller has been trimmed to reduced flow, then a new impeller of the correct size must be purchased and installed. You have seen that, in the traditional solution, energy is wasted by throttling a balancing valve or trimming a pump impeller, as both methods lead to some energy reduction. So we see that, by throttling a balancing valve, there is a wastage of energy. And by trimming an impeller, the impeller cannot be resized. So, how to overcome these problems? It's where the Danfoss solution comes into play. In Danfoss solution, the best energy savings are achieved by installing a VLT HVAC drive to the system. When multiple chillers and primary pumps are installed, variable speed drive control can increase energy savings and control. The Danfoss solution provides optimum primary pump flow and improved chiller efficiency. The most common method of control is to simply install a VLT HVAC drive on the primary pump. If a balancing valve is installed, it is partially closed to compensate for the impeller being too large and providing too much flow. After installing the VLT HVAC drive, the system balancer simply opens the valve and sets the pump speed to provide the design flow. Opening the balancing valve in the pump discharge eliminates the artificial pressure drop, and the pump operates at a slower speed to provide the design flow. If multiple chillers are used in parallel, different speeds can be programmed into the VLT HVAC drive, depending on the number of primary pumps in operation. In Danfoss solution, during commissioning, the VLT HVAC drive is used to reduce the pump speed to set the pump flow rate to chiller's design flow rate. This saves energy compared to using a balance valve. Take a look at the graph. It shows the comparison of balancing valve and Danfoss solution. You can notice from the graph that, in Danfoss solution, there is a lower pump speed curve at design flow. Thus in Danfoss solution, a lot of energy is saved when compared to traditional method. Sometimes, a flow meter can be used in order to measure the flow to the chiller. This flow meter can be used by the VLT HVAC drive to provide optimum flow. Using the built-in PID controller, the VLT HVAC drive will always maintain the appropriate flow rate, even compensating for changing resistance in primary piping loop as chillers and their pumps are staged on and off. Some chiller manufacturers promote variable flow primary loops as a solution, providing increased total system efficiency. For example, the chiller controller determines that the optimum flow rate for best efficiency is lower than the existing flow rate. It adjusts the set point for the VLT HVAC drive for the new flow rate. The VLT HVAC drive controls the flow rate using the set point and feedback from the flow meter. Take a look at the graph. Point 1 is the original required chiller flow rate. When the chiller controller requires less flow, the VLT HVAC drive reduces the flow to point 2, and this graph represents the reduction in energy consumption. At another time, the chiller controller will require increased flow rate, set point, and the VLT HVAC drive will change the speed of the pump to match the new flow requirement. Now, let's see the pump efficiency curve obtained in Danfoss solution when compared to trimming an impeller. A VLT HVAC drive improves the pump efficiency and saves more energy than trimming a pump impeller. A pump manufacturer plots the efficiencies for a pump with different impeller sizes to help the designer select the proper pump with a high efficiency. Take a look at the graph. It shows the pump efficiency curves for a pump with different impeller sizes. Please notice the best efficiency point for each impeller. Operation above or below this point is less efficient. An example of trimming an impeller is shown in blue point and red line. A pump with a large impeller would deliver excess flow at the system total pressure. By trimming the impeller, the size would be reduced from 250 mm to the smallest 200 mm impeller size. The point of pump operation would move diagonally as shown, with the pump efficiency decreasing from 80% to 75%. Take a look at the graph. It shows how the pump best efficiency is maintained with Danfoss solution. When a VLT HVAC drive is installed, a new series of pump curves at various speeds is created for each impeller size. The region of best efficiency lies in the system curve that passes through the origin. As the pump slows down, it moves down the system curve, and the efficiency remains constant at 80%. Thus, less energy is consumed compared to trimming the impeller. We just saw that Danfoss VLT HVAC drive facilitates energy saving. In the application, overusing balancing valves or trimming the pump impeller. To calculate the potential savings over time, the actual load versus time profile must be known. The load profile indicates the flow required by the system in order to satisfy its load during a typical day, month, year, or the time period under study. Take a look at the graph. It shows the energy consumption over time for a typical load profile of a primary pump for a traditional solution and the Danfoss solution. The profiles are flat because the pump provides a constant flow to the chiller. The difference in area is the power over time used by the pump when running. The profile varies depending on the specific need of the system and geographical location. Let us summarize the main benefits of using a VLT HVAC drive in primary pump systems. Here they come. VLT HVAC drive eliminates pressure drop of balancing valve. VLT HVAC drive provides higher efficiency over trimming the pump impeller. Energy savings are simple to estimate on using a VLT HVAC drive. Before ending this module, let me give you a brief summary of what we learned. In traditional method, we have seen that the use of balancing valve, or trimming in impeller, provides the correct flow through the chiller, which lowers energy consumption. With the Danfoss solution, the addition of VLT, HVAC drive, provides the correct flow, with a higher efficiency. We also saw the key benefits of using VLT, HVAC drive like elimination of pressure drop, of throttling valve, higher efficiency over trimming, simple estimation of energy savings,